Good morning, and thanks to the organizers for inviting me to give this talk. I'm going to take you away from the lab and oceans to much larger scale stuff in astrophysics. So I'm going to talk about applications of plasma physics and macrohydrodynamic modeling to understanding our space environment, as well as this applications to very new and emerging topic, which is known as star-planet interactions, which is relevant in the context of exoplanets and the habitability of exoplanets. And I hope to give you an understanding of how these MHD models are helping us, both in terms of applying basic fundamental science to assess space environment and protect our technologies in space, as well as to look at more esoteric topics such as habitability in faraway exoplanetary systems. Okay. So this is not a simulation. This is an observation. This observation is based on interplanetary scintillations from the Radio Astronomy Center, Ooty. What you see here are plasma transients in the heliosphere, which are originating in the sun, which has been placed there by hand, moving past the Earth's orbit, up to about 3 AU, so 3 times the distance from the sun to Earth. That's where the observations are done. This is due to my colleague P.K. Manoharan, who was at RSC Ooty once upon a time. So what this tells you is that the space environment that we inhabit, that planets inhabit around active stars, is a dynamic environment which is constantly changing. And what you're seeing are plasma density perturbations because of plasma winds and magnetized plasma storms from the sun, which can in principle go whichever direction in 4 pi around the sun. And that sets the motivation in the sense that tells you that planets like Earth and other exoplanets which are orbiting their stars are living in a very dynamic environment which is controlled by the output of their parent star. And much of the interaction is actually mediated via plasma and magnetic fields, and so we are in business. The sun is a magnetic star. What you see here are sunspots. This is the magnetograph image of the sun, which maps the magnetic field on the sun's surface. And if you look at a cotemporal, so taken at the exact same time, extreme ultraviolet image of the sun's corona, you will find that the corona is extremely bright and hot and radiates in extreme ultraviolet as well as X-rays, co-spatial with the underlying magnetic hotspots, which are known as sunspots or active regions. In fact, we know now that much of the outer atmospheric dynamics in the sun's atmosphere, which is known as the corona, is driven by magnetic fields. So these magnetic loops, they emanate out of the sun and they arch into the outer atmosphere. And the foot points of these magnetic loops are being constantly churned because of turbulence. So waves propagate up along the loops. They move around because the plasma beta is high in the photosphere and below, and they can physically move the magnetic fields around. And sometimes there is also magnetic reconnection. And when magnetic reconnection happens, the field lines can completely destroy each other. So there is a lot of release of energy which hits up the outer sun's atmosphere to 1,000,000 degrees and can also spawn energetic phenomena such as solar flares and coronal mass ejections, which has its origin in these magnetohydrodynamic processes. So what you see here is an example. This is an observation from the Solar Dynamics Observatory. The Earth is not there. It has just been put there for context to depict the scale of these magnetic storms. So these coronal mass ejections eject vast amounts of magnetized plasma from the sun, and they're typically associated with flares, and the energy that is released during the release of such a storm is equivalent to something like 500 million nuclear explosions happening at the same time. These are not always directed towards Earth. Sometimes they are. And when they are, they can perturb our space environment and disrupt the upper atmosphere and magnetospheric system. I'll be talking more about that. When they do impact the Earth's upper atmosphere, they create what is known as geomagnetic storms. One of the beautiful manifestations of geomagnetic storms are auroras. And what you see here on the right-hand side is an aurora over the northern polar regions imaged from the International Space Station. So this movie is taken from the International Space Station. On the left is the NOAA Space Weather Prediction Center simulation of the extent of the geomagnetic storm due to a coronal mass ejection impact on the Earth's magnetospheric system. So this kind of simulations, modeling, and predictions are now becoming very, very important in order to understand the variability in our near space environment. Why is that so? It is because this variable space environment determined by this activity of the sun, which are mediated via imagery processes, has a cascading effect right from satellites which are orbiting the Earth to air traffic over the polar routes, to disruption of GPS navigational systems, communications, both satellite-based as well as high-frequency communication that is used by the defense. And in high-latitude countries, they can also sometimes result in power grid failures because of the induction of geomagnetically induced currents. And they can also sometimes result in fires in oil pipelines, essentially large conductors, which through Maxwell's equations, if you have a varying magnetic field, you can induce voltages and drive currents across these large conductors, and they're not good for electric power grids and oil pipelines. And when the storms are moderate to serious, they can combine with certain other attributes of satellites to result in catastrophic deorbiting. And this was witnessed about 2 years back in 2022 when SpaceX launched 40 Starlink satellites to a geomagnetic storm, and I'll have more to say about that later. So if you ask the question, as a country, Indians, which is a low-latitude country, we don't see auroras, we are not in the northern regions, should we be worried about the space environment? Should we worry about space weather? The answer is yes, because we are a satellite-dependent nation. Much of our navigational needs, communication needs are driven by satellites. And I've listed certain sort of domains there. So satellite operations, telecommunications, navigational networks, astronaut safety, aviation, offshore drilling, and many of the high-frequency communication that defense and disaster management services use are all susceptible to space weather, and India is dependent on that. Except the electric power grid failures and oil pipelines, every other aspect of the impact of space weather is felt by a nation like India, and therefore it's very important for us as well. So when I came back to India about 15 years back from the US, the field of modeling, applications of models to space weather, data-driven models and space weather predictions was essentially non-existent. And we started it off in India. I'll give you a couple of examples from our work, but before that, we also observed the Sun Earth system. And this is very crucial because you can't just build theory and models without really confronting them with observations. And if you're making predictive models, you have to drive them with boundary conditions, and they come from this satellites. So there is roughly about 3 dozen satellites now, mostly by NASA, IISER, some by JAXA, one by the Chinese Space Agency, and now one by ISRO, which is the Aditya L1 mission, which was launched in 2023, which is a space-based observatory to look at various aspects of the sun, starting from imaging it remotely to looking at the in situ plasma and magnetic environments at Lagrange point L1. Well, right, so now we will come to our work with that broad introduction, because I thought that's important given that we're talking to an interdisciplinary audience here. My work primarily relates to the physical understanding of the Sun Earth system, and I'll try to give you a window to how we build our models and what is the physics that we use to get a sense of what's going on in terms of the space environment. I will just talk about star-planet interactions here and not worry about solar activity per se, which is the other half of the work that I do. Well, astrophysical plasmas are very different in the sense that very large scale. And given that they're very large scale, the magnetic Reynolds number in these systems are very large. One can think of it also in this way that flow timescales essentially are much shorter compared to the diffusion timescales. So magnetic fields can remain frozen in the plasma and they sort of move together. One other very important parameter is the plasma beta parameter. So it's a ratio of the magnetic pressure to the fluid pressure or gas pressure. So whether it's greater than 1 or lower than 1, to a large extent determines whether it's the fluid flow or the magnetic fields which is governing the dynamics of the system or the particular domain that we're interested in. There's some other physics that is also very interesting, which is the physics of magnetic reconnection. So you all know about turbulence and waves. Magnetic reconnection plays a very important process as well in astrophysical plasmas, because often when you have magnetic field lines frozen in the plasma and you have plasma flows which brings together field lines which are not perfectly aligned or are anti-aligned, so anti-parallel, then magnetic reconnection is favored. And this is a beautiful process of conversion of magnetic energy to other forms of energy such as thermal energy, energy to accelerate particles, heat up materials, and also drive strong turbulence in the regions where the shear in magnetic field is very strong, which are known as current sheets, because the current is extremely strong in this particular regions, and they exist in multiple different domains that we are going to talk about. Well, the challenge of looking at star-planet interactions is based on which domain, from the sun or the star to the planet you're looking at, is characterized by different physical parameters that characterize the environment. So more or less everywhere you're looking at magnetic Reynolds number, which is pretty high. So magnetic fields and plasma still sort of, tango together and move along together. However, if you go to the sun's interior or star's interior, by virtue of the fact that the pressure is very high, given that the density of matter is very high, you're looking at a high plasma beta system. So there the flows, the plasma flows govern the dynamics of the magnetic fields. In fact, the energy of the flows is channeled in to producing what is known as magnetic fields through a mechanism known as the dynamo mechanism, which is another field I work on, which I'm not going to talk about tomorrow. So the sun's magnetic fields are produced in that region. When they emerge, they are in the low density solar corona, where the plasma beta parameter is low. And there is the magnetic field which governs the dynamics of the atmosphere. So evolution of the magnetic fields, magnetic field movement, they move along the plasma, and magnetic fields is essentially the boss in the sun's corona. When you're a little away from the sun's corona, away from the sun, the solar wind becomes supersonic, and the dynamic pressure of the solar wind now becomes stronger than the magnetic pressure. And then again you hit a regime which is high plasma beta, where the solar wind essentially opens up the magnetic field lines of the sun and carries them away, and then eventually when it interacts with the planet, it encounters a magnetosphere or the lack of it, but certainly an obstacle, and then there's a lot of fun interaction that goes on there. Let me talk a little bit about what happens when the magnetized solar wind interacts with a magnetosphere. So you have the solar wind coming, let's say, assume it's coming from the left. This is a cartoon, the sun is on the left. And then you have the planetary magnetosphere, let's assume that's Earth, with a magnetic field. This planet has a magnetosphere. Okay, so when the solar wind hits, remember that in principle, if you cannot stop the solar wind is essentially going to blow away the atmosphere, right? The magnetosphere and atmosphere will be blown away. So what maintains this balance? Why is it that we have an atmosphere? It is critically dependent on the maintenance of a balance which is governed by the thermal pressure, the magnetic pressure, and the dynamic pressure of the solar wind being balanced by the thermal pressure and the magnetic pressure of the Earth's atmosphere magnetosphere system. And when that is achieved, that's where you have a region known as the magnetopause. The bow shock is also located there, where the squeezed magnetic field lines of the Earth has higher magnetic pressure, and that plus the thermal pressure of the atmosphere can literally stop the solar wind from penetrating closer to the Earth. So that's the theory, of course, and then there is, in that boundary, there is also turbulence, there is magnetic reconnection. So a lot of important processes is governing what's going on in that magnetosheath region. But I will keep this story simple and not make it very complicated, and I translate this to simulations. And these are some of the first models. This is in fact the first star-planet interaction model that was built in India about, I think, 5 years back. So I collaborated with some students, a postdoc, and Vargav, and we built this model. NASA had these models, the European Space Agency had these models. This is the first Indian model to look at the impact of a supersonic magnetized plasma wind on a planetary magnetosphere-atmosphere system. So the plasma wind is imposed as a boundary condition from the left-hand side, and the Earth with the dipole an atmosphere which is sitting on that out there, you can see it. What you see here clearly is a bow shock formation when the plasma winds hit the Earth's atmosphere, and the bow shock region essentially captures that physics of compressing the magnetosphere. And then when the magnetosphere gets compressed, the magnetic pressure increases, and this whole equilibrium of pressure balance comes into play. And this happens at about 5 to 6 times the Earth's radius. And remember that the Earth's atmosphere, which I have just put there by hand, it is really much thinner than that, but I have just showed it there to give you an idea of why is it that the Earth's atmosphere is so protected. It's only 60 kilometers. It's a very thin, fragile atmosphere. But it's this magnetohydrodynamic interactions and fluid interactions and the physics of this bow shock and the fact that we're being able to stop the solar wind by virtue of having a magnetosphere is what protects the Earth's atmosphere. And this is very important for habitability. Here is an example of what happens if you keep increasing the solar wind speed. The more you increase the solar wind speed up to 8 times, the more the magnetopause region shifts closer and closer to the Earth's surface. Now you can ask the question, what happens if the planet did not have a magnetosphere? And we explored that as well to look at the loss of the Martian atmosphere. And this is exactly what happens. So when you don't have a magnetosphere, there is an imposed magnetosphere. But the imposed magnetospheres are not the intrinsic magnetic fields of the planet. It's the magnetic fields of the stellar wind wrapping around the planet. There is still a bow shock. But this magnetic plasma, which is around the planet, is constantly slipping past it. And it's constantly slipping past, it viscously couples to the planetary atmosphere and slowly erodes it away. And over a long time scale of millions of years, this would result in the loss of a planetary atmosphere. And it is thought that Mars actually had an atmosphere and a magnetosphere up to about 1.5 billion years age, but subsequently, due to certain processes, its core froze and the magnetic dynamo died, resulting in the loss of the magnetosphere, subsequent to which it slowly lost its atmosphere to the solar wind. So these are examples of star-planet interactions, how this is crucial for habitability and ability to hold an atmosphere in the solar system. Now you can ask this more profound question, what about life, and what has magnetic fields and imagery processes got to do with life and habitability in other planets? I will motivate that question first. So there is more than 6,000 exoplanets which has now been discovered. And about 4% of them are Earth-like, implying that we have about, I think, 300 Earth-like planets. We have some information about the magnetic fields of stars because we can look at either X-ray proxies of the magnetic activity or through a very interesting observational technique called Zeeman Doppler imaging, we can directly measure the magnetic fields of stars. But planets are too small. The magnetic fields of planets are also very weak. So essentially, we don't have any idea about the magnetic fields of all these planets. So then you can be a theorist and wear your theorist hat and ask the question, okay, so let's assume that I have a zoo of magnetic fields of stars and a zoo of magnetic fields of planets. So given that scenario, how can I address this question of what controls the ability of a planet with different magnetic fields to hold on to its atmosphere given a star with different magnetic fields? It's a beautiful intellectual question to ask. And why is this important? It is important because we know that for exoplanets, the primary forcing of exoplanetary atmospheres happens by stellar activity, which is stellar winds, stellar magnetic fields, stellar radiation and energetic particle events, and sometimes stellar flares and stellar coronal mass ejections, right? And all of these actually owe their origin to the magnetism of the star. So when you look at observations of the magnetism of the star, I have two examples to show here. One was what we did long back, which is indirect, looked at X-ray emission from the star, and X-ray emission, the flux of X-ray emission is very directly coupled to the flux of magnetic fields on stars, and construct how does a star age with time by looking at different solar-like stars at different relative ages with respect to the sun. So what you see on the x-axis is basically age. The sun is marked in yellow on the left-hand side. On the left is younger stars, on the right is older stars. So sun is about 4.5 billion years age. More recently, in 2014, this work was repeated with this new technique that was discovered called Zeeman Doppler imaging, where they could directly image the magnetic fields of different stars. And you see the same effect, which basically shows that for a sun-like star, with age, its magnetic field is reducing. And that's not surprising, because angular momentum losses slows down the rotation of the star, which then also slows down its differential rotation. It reduces the dynamo efficiency, so the magnetic field changes. If you also look at the zoo of stars, particularly on the right-hand side plot, you see that different stars have different magnetic fields, right? So this tells you that I can have a planet around a star which has, based on either its age or the type of the star, very different magnetic fields. And then I can assume that a planet has different magnetic fields and do simulations to see what happens when I have star-planet interactions with differing stellar and planetary magnetic fields. I'm going to show you an example of a dynamics here, where the dynamics is very different from what was going on Earth. Here what is going on is the formation of Alfvén wings. So, you see, so Alfvén wings are named after Hannes Alfvén, the only Nobel laureate in MHD, for his fundamental contributions to the early pioneering work that he did in magneto-aerodynamics. So the magnetosphere of the planet is being ripped apart and forming these beautiful wings, which are called Alfvén wings. This happens only in the subalfvénic region, when the alfvénic
it is yes. 23 minutes.
Okay, so I have 2 minutes to complete my talk, right? Okay, so when the wind speed is essentially the time scale of the wind speed is lower than the alfvénic time scale, what happens is the interaction is primarily electromagnetic. So even upwind, so before the stellar wind hits the planet, Alfvén waves carry the information, and this is so beautiful, that a planet is in its wake. And then this wind, this wings become, start opening up, and they open up all the way to the front part or upstream part of the planet. And this results in much more violent mass loss. We did a parameter space study of this, and these are the numerical experimentation, what you see here. What we found was that given the same planetary field strength, a stronger stellar magnetic field strength will result in higher mass loss. Mass loss is on the y-axis here, the ratio of the planetary magnetic field, and wind magnetic field is on the x-axis here. But surprisingly, if you have the same ratio, but higher magnetic field for both the planet and the star, there is also higher mass loss, and we explored that in great detail, and it turns out that the reconnection surfaces, when the magnetic fields are stronger, are larger. And when the reconnection surfaces are larger, there are much more leaky areas through which you can actually lose the atmospheric mass, resulting in higher mass loss of the planets. We also worked out a semi-analytic formula of predicting this, and it turns out that it fits the numerical experimentation fairly well. So this is sort of a semi-analytic scaling relationship established between the stellar magnetic field strength and the planetary magnetic field strength, which tells you how atmospheric mass loss rate of the planet is determined by differing magnetic fields of the star and planet. So this is completely intellectual, completely esoteric, but quite nice because we managed to also match the simulations with this semi-analytic relationship. Finally, I'm going to take 2 minutes and end with the loss of the Starlink satellites in February 2022. You see them entering the Earth's atmosphere and burning out. This is a big surprise because it was completely unexpected. I'm going to give you an example of how we can also use MHD to figure out the deorbiting of satellites in the face of a geomagnetic storm. So we wrote 2 papers on this. The first one in Abjay Letters by PhD student Shobhik was to figure out how to understand the onset of a geomagnetic storm when a coronal mass ejection impacts the Earth's atmosphere, and Bhargav also is now working in this domain. The second one was a collaboration that I initiated with students at our institute and some scientists at NASA and Predictive Sciences Inc. in the US to actually explain the losses. I'll very quickly just say that what we did was we did data-driven simulations where data from
So your question time starts now.
yeah, in situ. So in situ means at Lagrange point L1 was fed to drive the models. And from the models, we could figure out the geomagnetically induced currents, the ring current enhancement around the Earth's atmosphere. And this current density enhancement results in heating due to the collisions that when the current is being driven in the Earth's upper atmosphere through the neutral atoms, and this heating makes the atmosphere rise. This increases the drag on the satellites and they lose energy, and based on the ballistic coefficient of the satellite, it can react differently, and the Starlink satellite's ballistic coefficient is not so conducive. It has a large surface area to mass ratio, and so it could not withstand these geomagnetic storms, and it essentially fell from the sky because it's lost energy due to the enhanced drag due to the rise of the atmosphere. This is what happened during this solar magnetic storm. So with that, I'll stop and I'll just leave this slide with the key takeaways. The important thing is that stars influence our space environment and technologies. It also, over very long timescales, actually, through MHD processes, influence the possibility of life, and that is something that is profoundly beautiful if you think about it. And I will stop there. Thank you.
Thank you, Devendu. Any questions?
I am Pralay Kumar Karmakar from Department of Physics of the Espore University. So thank you very much for your nice and informative presentation. So in one of your slides, I found that you mentioned that young stars are magnetically more active, and with age, the magnetic intensity or magnetic effects are dying.
That's right.
So the last stage of sun or sun-like stars are, as all of we know, white dwarfs. But typically, white dwarfs have magnetic field on the order of 10 to the power 5 to 10 to the power 9 Gauss. So it is the last stage of sun or sun-like stars, still that it has significant magnetic field. So I would like to know the physical mechanism inside.
Yeah, so it's not a dynamo, so that just simply follows from flux conservation. At the end of a star's lifetime, it collapses. If you just take a 10 Gauss, even a 10 Gauss or a few Gauss fields, crossing the equatorial surface and collapse it to 10-kilometer radius, flux freezing will ensure that you end up with a 10 to the power 12 Gauss field. So that's trivial, it's not dynamo, it's just flux freezing. Collapse of the inner part and the flux is conserved, so it just gets compressed in a smaller area, the field strength increases. That's it.
Okay, thank you.
Okay.
Welcome.
I'm MP Bora from Guwahati University. Thank you very much for your nice talk. I was just wondering that you were showing that wings, the Alban wings that in the last of the slides. So that's happening, it's a purely dynamical, or it's because happening of the magnetic reconnection in the tail region?
It's a dynamic effect, of course, and it happens actually in the solar system. It also happens in one of Jupiter's moon, Io.
But we don't see in our case, we don't.
No,
see
you will not see that, because in the Earth's case, the solar wind speed is much higher. So you really the Alban Mach number is much higher than 1.
Okay, so that
So
means
it doesn't happen or not.
So
no.
that means it's a slower speed on that.
Yes,
Jupiter's
you
moon.
need slower wind speed and higher magnetic field strength
Magnetic field.
Yeah.
Okay.
for this to happen.
So it's not an artifact of magnetic reconnection and kind of.
Oh,
things.
it's certainly not an artifact. This is a known
No,
physics.
I mean artifact means it's not effect of magnetic reconnection like that.
No, it's not a magnetic reconnection effect.
Okay.
No,
Right.
no.
Okay. Thank you.
But it induces magnetic reconnection when it's opening up.
Right.
Hi, I'm Subham from IISER Center of Theoretical Sciences. Nice talk, by the way. My question is about the MHD term. So
MHD?
MHD term, because in your simulation you covered a long scale from the magnetopause to magnetotail, where the densities vary a lot, and hence the plasma could be collisionless in principle. So how do you, say for example here, starts from magnetic pause to the magnetic tail, where there will be collisionless processes, particularly the magnetic reconnection you talked about. So these are the result of these collisionless processes, particularly in the magnetic pause and magnetic tail region. So how do you incorporate these in your
Right.
yeah.
Okay. So to answer your first question, so the particle density here around the planet is governed by the atmosphere that we put in, which is initialization process. So essentially, we have a wind, atmosphere which is balanced in a way that it reaches pressure balance at about, I would think, about 1.5 stellar planetary radius. I think that's what I recall. So it doesn't have an outflow. So that's how we start off the simulations. Your second question was, and the solar wind density is something that is assumed to be constant. Your second question was, is MHD is a valid approximation or not? Was it what you're trying to say? Yes. So given that we are essentially simulating very long time scales and very large time scales, you can essentially do a hand waving back of the envelope calculation to show that MHD is just fine here.
Hi Dipyendu, this is Ganesh here. Very nice talk.
Thank
Curiosity, normally you also have a lot of neutrals in the system, right?
Yeah, we have not considered any neutrals.
Is that important for your overall story? I mean,
It is important in the sense that if you want to have a very true handle on mass loss, you should ideally consider a two-fluid system. You should have neutrals, because then you have an additional viscous term that's coming in, and that's a more truer sort of way of representing the coupling between the neutral atmosphere and the plasma that's outside, rather than having a plasma domain all throughout, right? So yes, and I think that what we are doing here is we are overestimating the mass loss rate. Qualitatively, we are doing fine, no problem. But quantitatively, we are certainly overestimating the mass loss rate because we don't have a neutral fluid, where the viscous coupling will be less efficient than a plasma atmosphere coupling to a plasma. So certainly, yes, I think quantitatively it will certainly make a big difference. We'll just have one more equation for the neutral fluid and many more coupling terms which are unknowns to handle.
Thank you, sir.